Should be live. So yeah, I'm just doing a quick unplanned stream because I figured I might as well tick off some of the items that we had left in the for the M2. So give me a second just to make sure that my capture. Also, no camera this time. I'll just keep it simple. I mean, you already know it works, and like like the penguins already showed up, so I don't think we really need the camera. I'll just do everything over SSH and the serial port, and you won't miss anything interesting. Let me just make sure that nothing weird is going on here. So today I'm going to be working on the SPMI and PCI Express. Well, PCI Express, I think I only need to have to add the fuses, the fuse map, which is just that little table of like what bits go where that goes in Mini. So that should be pretty easy. But I need to reverse engineer it from the Apple driver because it's basically dumb. You know, there's no reason not to do that. So let me just make sure this is all sane. And the other issue is that SPMI is the SPMI hardware changed, so I need to write a new, well, at least effectively a new driver, or possibly change the existing driver. Make sure I'm the right thing here. Yes. Oh, hey Joy, thanks. I can buy a Mac Pro. I think I'm gonna need a little bit more than that, but a Mac Pro. But every little bit helps. So yeah, let's see. Make sure I got everything right. Yep. All right. So yes, the issue is that okay, now I can turn on everything. Yeah, it's on a stream, so like nothing is like set up. So here's the thing: the SPMI is a MIPI Alliance protocol, and like all MIPI Alliance protocols, the specifications are top secret, and yeah, you can't get them. So Linux does have a MIPI subsystem, an SPMI subsystem. Which mostly tells us what we need to know, but it's often, if you're looking for information on a protocol that is from the MIPI Alliance, the best place you can get some hints is documentation for people who make protocol analyzers like this one. Because although it's not a full spec, it does give you, some examples of what commands look like and how they're supposed to be decoded. And, from these screenshots, you can usually get a decent idea. So this is nice just so that we understand. Thanks, more thanks. Don't overdo it, Joey. Thanks. What's up with my sleeping schedule? Yeah, it's messed up as always. Yeah, so here's the thing. These traces are pretty useful for just kind of understanding how it's supposed to work. So that's why I just Googled a bit and found some PDFs with, like lists of commands and transaction examples and stuff like that. So that's cool. So we have that. But first I'm going to look at PCIe. So here's an old Ghidra for the M1 PCIe that I had lying around. I don't know why I have this open twice. But I'm looking for this structure. I think Sven or someone else figured this out the first time. I don't remember. It wasn't me. But basically, Mini has this table here. And so there's one for M1 and one for M1 Pro and Max and Ultra. Actually, it's possible that M2 actually literally has the same one as M1. We'll find out pretty quick if that's the case. I mean, this is not going to be a 10-hour stream, by the way. Don't expect that. But I might stay up until 3 a.m. But I'm hoping this doesn't go too poorly and we actually get some progress, because I don't expect sort of terrible things, the famous last words. Yeah. So we have this table, and it's literally just a table that says take this number of bits from this, fuse offset, stick them into this offset in the PCIe register. That's it. that is all this is. And it's just, you have to copy those bits from A to B to configure the physical interface for the specific like electrical characteristics of this particular chip, because these are calibrated at the factory. And yeah, like, I mean, you can see with the hypervisor macOS doing this, but you can't tell which bit goes where unless you start like intercepting the fuse reads and giving it test patterns. And like normally we avoid reverse engineering Apple drivers for copyright reasons. But in this case, like even if I did it using the hypervisor, it would just be a long-winded way of getting to the exact same result and the exact same table. And the structure isn't literally the same, though. You'll see in a second that the Apple uses a different structure for the table, but like the data is the same because it has to be the same. So yeah, this is just kind of pointless. Like this is the fact that on this hardware, these bits have to come from A and go into B to make it work, and there's no going around that. And it's not copyrightable because facts are not copyrightable. The specific layout could be copyrightable, which is why this one is a different layout. And yeah, that's pretty much it. So the first thing I need to do is actually get the new driver, and I don't have that. I think the version of macOS that ships with this still has the checks, because I believe they stopped shipping those and they put them in the KDK now, which is a bit annoying. So one thing I'm going to do is actually just I think we have a actually I can just look at that. Oh, that stage didn't work. Well, I can just pause that and hopefully catch it before it initializes. Wait, that didn't work. Did it just break something? Wait, that's not... Hold on. Something really weird just happened. Oh no, that's the serial. That is supposed to look like that, but... Hold on. Is the hypervisor broken now? Yeah, that'd be lovely. Yeah. Hopefully it's not very broken. But let me check to see how... I forgot how you get a shell the first time around. Roxy client tools, run guest. It was capital S, but it has to go before that. Probably before the Mako. Is the hypervisor broken all of a sudden? Or is this because I'm not running the... No, I am. I did merge the everything. Okay, now see, now we have a different problem. What? Oh, it's the PMU thing. I keep okay, yes. Yes, the thing I'm fixing today is the thing I'm fixing today is the thing that that I have to disable because it's obviously not going to work right now. Oh, never mind. Yes, this is not working as intended. Yes, no, it's fine. Yeah, so let's get the shell on that. Let's do a quick trace of the PCIe registers. Let me remind myself of where those are. Those should be fuse bits. Those get applied to fuse base and then get written to phi IP base. And so phi IP base is the third register in APCIe. So we're going to go u.adt/arm/io/apcie.getReg3. That gives me what I want. Actually, I can just do trace. I can just trace the whole device, to be honest. And we'll see what happens. And I can just start it. And I'm going to have to actually then go into macOS and pull this out. So we got some in it there already. I'm going to stop it just so it doesn't spam if there's more stuff. Because this could actually be the same as M1 if they just reuse that, or the same as M1 Pro and Max. It'd be very lucky if that's the case. So there we go. So the stream is, we're looking for 3, 2, 3, 5, 2. I don't see 3 yet. Unless this changes. I know this, no, but this is per port. Oh, is it per port? No, wait. No, that those are globals. They go on 5P base. That is actually, no, it is 3, sorry. Yeah, 3. So we didn't get that yet? Unless this is different on this one. Actually, what is that 2 stuff? Phi? This looks like it's modifying registers, but not from fuses. Unless the fuses, no, but they do read it from here. Oh, unless these overlap, which could happen. Let me just look at that. So we are looking for 3. Let's get that in hex. 6 at C00. Okay, no, so those are not that. Definitely. Yeah, it starts at C8, so those are something else. Let me just let it run. Oh, okay, there's more. It should be initialized by now. Okay, did PCIe end up with a new register layout? That would not be completely unsurprising. But if so, that's another thing we need to fix in Mini. So in here, let's look at the ADT again. Hey, PCIe, let's see what we have. And just compare this to M1 and M2, and that might give us some hints. So if I look at the ADT, TXT, PCIe, and this is what we have for M1. So the first one's the same, second one's the same, third one's the same, fourth one's the same. Okay, those are the same. The lengths are a bit different, but that's okay. And definitely gained a port, but we were kind of expecting that. Okay, that's either I'm missing something obvious, which is entirely possible, or something is a bit different here. Or I failed to trace that properly. Hold on, let's see what we have in the log right now. Yeah, I don't see 3. Okay, that's weird. And the offsets which we're reading from, actually, just to make sure we're not off of that. This is taking fuse bits, target register is just added, and we are expecting for the M1 in the 6000s. So that would be 68 C 6000 or something like that is the range we'd be looking at for the fuses. 68, not 69. Oh, there we go. Wait, but 4, 5, 6. That's not quite right. I don't remember M1 being like this when I looked at this. Yeah, so these look like that. No, the PCIe I think is the same as M1 Pro and Max. So I do expect that to look around the same. And these didn't actually change that much. Like a lot of registers are duplicated anyway. The fuses are different. That's not unexpected. And then actually the fuses here you can see are 5, which is 0, 1, 2, 3, 4, 5. Yeah, 3 to DC. And actually that's a hint because yeah, these are the fuses. And it's reading 4D8 many times. That's like I'm not tracing the this is the fuse sequence because it's reading that many times over. And then it's like I totally missed the writes. Yeah, it reads more and then nothing. Okay, what's going on here? Did I actually trace everything right? So we have it 6800. I'm looking for OOC print tracer. Yeah, that's right. Yeah, we're getting these, right? At OOC. So like this stuff is getting traced. And it is, wait, it is doing writes here. Oh, okay, it's because C. Okay, no, it's because register 2 also covers register 3. So that's why the coding is getting confused. Yes, okay, that's fine then. But that's interesting. Why does it do that without reading the fuses? Oh yeah, okay, this is the phi sequence. So you can see it's writing to, got that in order here. Yeah, so this is that. 580, 94 AC, 52, yeah, 522C is in there, right? It's slipping some bits there. 62A4 is another one that it reads, and then something happens. It doesn't write it though. That's interesting. 6238, 52A4. Yeah, 522C. It's also in there. Got some bits changed. 5278. Yeah, that's in there. So that matches. But then I don't get why it's not reading the fuses. Because it's like it goes and reads the fuses afterwards. But that doesn't make a lot of sense. Unless it's reading another set of fuses. So that's on 5. 5, yeah, 3D3, yeah. It should be that one. 1100. Are we actually tracing that properly? Because it's not aligned. Wouldn't surprise me if we're not aligning that properly. 3D2C. Oh, wait. Oh, is it because something else untraces that? The 3D2C. No, 81211. No, it is on print tracer. 23D2C 8000. Oh, wait, no, it is here. Oh, okay, I guess it reads the fuses first. And it's reading 4C4 and 4D8. Yeah, okay, so look, it's really close to the M1 fuses. It's not the same, but it's really close. So it probably just reads these ahead of time. And it only needs these two, 4C4 and 4D8. And that's actually the same as the Pro Max. These also only had two fuses for everything for PCIe. And then the actual sequence where it writes it is these aren't chicken bits, by the way. These are phi like configurations, so it's not exactly the same thing. If they were chicken bits, they'd be hard coded in the driver, but they're not. This is like tuning parameters. So where was I? 8. Hold on. I'm looking at C 5 somethings. Yeah, these. Oh, but remember, there's actually there's two things, right? One of it, this is the tunables coming from the ADT, and the other is the fuses, and they should not be interleaved. Look. Oh, wait, no, here it is reading the fuses. And how did I miss that? This is the fuse sequence. I'm dumb. There we go. So it's reading from 490 and writing to 6238. Look, same as M1. And then 6220. Yeah. Then 6284. And then 5 8. Okay, that's a bit different. 5018, 5020, 5284. Yeah, okay. It's pretty close. I think for this one, for Pro Max, I actually sort of sorted the list, but not quite. I think I may have not kept it the same order as Apple had it. 6238, 522C, and then 1204, which yeah, it's also in there. Yeah, so this is very, very similar to the it reads from 494, 522C. Yeah, so yeah, let's just get the sequence from the driver. There's not much pointing in just trying to mess that. But I am going to copy and paste this, so I have this as a reference. That's the one. That's what we want. This is what we're emulating basically, but we don't know the exact. Basically, we have these. These are the the left-hand side of the table, and then this right-hand side is what we have to pull from macOS. So you know what? I might as well just write this out, so that I can say that some of it didn't come from the driver. T112, and so the fuses that we have are basically all 490. Sorry, 490, and then the last two are 494. How many do we have? Let's just put some new lines in here, make sense of this. So the way to do this without reverse engineering the driver would be to have the hypervisor like provide fake values like 1010 patterns and like and then 1100. That you give it a sequence like that, and you reboot macOS like I don't know 32 times or however many times it takes, and then you can compute the table from from those values, but you end up with the same data. It's kind of completely pointless. So this is 6238, 490. Yeah, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 at 490. 1, 2, 3, 7, 8, 9, 10. And then we have 2 more. So there's apparently 1 more than what we expect. So these are all 490. I'm going to kill... Well, I must leave them, but 490... 490. Wait, 3, 5, 6, 7, 8, 9, 10, and then 2 more. Yes. So there's one more set for this one apparently. And so 494. And then the targets would be 6238, which we have. 6220, which we have, 6284, which we have, it's all the same. 518, which is that one. 5220, yeah. 5220, 5284, 5278, 522C, 522C, 22C, 522C, and then the last one is 1204, which is the same as that. So yes, very, very similar. And you know what? I might not even bother using Ghidra for this because I already have the T8103 version. You can't read that, sorry. But I already know what the table looks like. I already know what some of the numbers look like, so I can probably just binary grep the kernel, find the table, and call it a day. And I don't even have to pull this from macOS. So we have 6238. And what's the yeah, so this is set as 3C84. Okay, yeah, so it's offset from the other register range. So we're looking for 3C plus the offset there. So yeah, the offsets are also a bit different from what we have. 3C084. I guess that's different on the... Yeah, but basically, we just... Yeah, and then 6238. Yeah. So it's one word for the source, one word for the bits and stuff, and one word for the destination, and one word for the bits and stuff for the destination. And it's 406 for that one, which tells you the source bit and width, and then it says 7, which I think is the target width, because some of them have a target width that is actually wider. We don't actually implement that, doesn't seem to matter. So then there's like A03, and then the other one is like E03, yeah. So we're looking for... actually, I can just look for 6238 7 probably, and that'll find it. So if I just go and take this kernel and just hex dump it and look for as a DORD, that would be 386. Oh, that's wrong place. 38620000 and then 07000000. I bet that we'll find it. Yep, there it is. And there's probably just one hit for that. Yep, looks like it. So don't even have to pull up Keydraw. Yeah, that's it. There's the one place. So let's just take that. And also, look, it's like right at the end of one of the Mako segments, because this is like the Mako header, I think. So that's also a hint that this is like that. Yes, let's just take that. Don't even need Ghidra. Put that in there. And this starts at, we said 490 we had in there. Yeah, there it is. Look, 490. 0006. So that's the same bit, actually. Oh, no, it's not. It's the low. It means width 6 starts 0. Okay, so it's from 0 or that one. Let me just... Let's get the widths right first. And actually, this is kind of offset, which is going to confuse me. So I'm going to reformat this. Just put it in like that. Makes it nice and easy. Get rid of some of the junk. Yep, 9004. 06, 07. Yep. Let's get the width right first. Then we have 3, 2, 1, 3, 2, 3, 3, 2, 4, 1, and 5. Doing it by columns like that makes it a bit easier. And then these are the source bit offsets, which would be the first number here. So these are 0, 6, C would be 12, E would be 14, F would be 15, 12 would be 18, 14 is 20, 17 is 23. 1A is 26. 1C is 28. And then we have 0 and 5. And finally, the target offsets would be 0, E, which is correct there. 17 is correct. I said 4 and type 5 for the fourth line. 4, 1. Where was I? Oh, you're right. Yeah, that's a 4 for the width. 2, 4, 1, 5. Yes, thanks for that. See, this is why I have you guys. I did number 12. I think you mean 10. All right, 0. No, I lost my place. 0, E, 11, 2 would be here. E, 14. 17 there. Another 20. 12. 9. 16. And, 20. And 2. And I would expect that to be also fairly similar to the first one. So we have 14.3, yep, 17.2. 2.1 is in a different order for that one. But then, yeah, that one's different. 9.2 we do have here, so that's good. For this one, we do have 2.1, yep. For this one, we have 14.3. For this one, we have 17.2. For this one, we have 23. For this one, we have 12.3 and 9.2 and 16.5 on this one. 4, and that's interesting. Wait. Did I get that wrong? Okay, that's interesting. That one's yeah, they have 4 for this one. They used to have a 5. That's interesting. It's like they dropped a bit. And it's both the source and destination too, so that's kind of weird, but shrug. And 21, which that's a new one. Oh wait, no, they just added that. Oh, okay. It's because the spans to this overflowed the fuse. That's why this overflowed the fuse, went into the next fuse, so it's a new entry to set the remaining bit. That's fine. And then 1204. Yeah, this goes after that. So yes, that's what happened there. Yeah, so that should work. And I'm just going to save and format that. Oh, I don't want it to do that. I forget how I fixed that. There's a thing. How was I making it not do that? There was like a specific trick. There's something different here. Wasn't it like the comma at the end or something? Oh, is it because this is on its own line? Is that why it is? Oh, that's why. Oh, that's annoying. Oh, it's because it's like just the right number for that to happen. I guess Clang format just has that rule. Like it only puts array. Can I change that? Align array of structures. Oh, it's only applied to arrays with equal number of columns per row. That should be fine though. It's an item max or something. Nah, maybe not. Yeah, I can put Clang format off. Oh, is it really only? Maybe it really is because it's an exact multiple. Maybe it's just like we got lucky. Or not. Yeah, okay. It's because it's because it has to be an exact multiple. So yeah, I guess it may just clank format of this. How do you do that? Is it just yeah? Yeah, that works. Let me just undo the other change. Okay, so that should make that work. And then I think is it T81012? Where is this? Hmm. Yeah, it's T81112, so that's easy. So that should take care of that. Hopefully, yeah. Let's just see if it works. So it could possibly go wrong. So I'm just gonna kill the hypervisor. Go back. Try Mac. Try Linux. And we're going to run guess. Also, this am I in the right branch? Probably not. No, I am. Yes. I did want to rebase this on Asahi. I did rebase this on Asahi. Now it's going to have to build. Make.sh. Let's run this again. This is not an NVMe one. Let's do one with the initramfs. The DTSs. Run guest mini Linux. Yeah, that looks right. Earlycon, all that stuff. Yep. Thankfully, C cache is taking care of most of it. So that's not going to take long. Where's my console, actually? Do I have a console? No. Where am I? That's the CH340. Oh, it's here. Okay, there's no PCI. Did okay? I don't see PCI, so I think that. Oh wait, no, I did turn PCIe off. Yes, let's not do that. But actually, what did Mini say about this first before Linux? Okay. Yeah, initialize the single port, which is what you expect. Knock speed 2. Okay, that looks good. So yeah, I just need to fix the. I just need to actually enable it because I turned it off because it was crashing before. This is T8. I think I closed that. Oh yeah, the pins. Oh yeah, the clock regs we don't have, but that's okay. We'll figure that out when the like Mac M2 Mac Mini comes out. PCIe Dart status disabled. Do not disable this. Do not disable this. Just try again. I see PCI. I see Broadcom trying to load firmwares. I know the firmware. I don't have the firmware for this board, so that's not going to work. I think PCI works. It found the Broadcom. Yeah. It just probably failed to load the firmware because we're missing that. So I need to actually go to macOS to pull that off. But yeah, this is working as intended. So there we go. PCI works. Yeah, there's nothing but Wi-Fi here to be used. So that's all you expect to show up. Okay, let's go back to macOS. Just pull the firmware out. See, I told you it was going to be easy. Okay, I can commit that while macOS boots. macOS has booted. I think I don't even have SSH turned on here, so just give me a second while I type on the physical keyboard. Can I SSH in? Can I use local for this? Is it going to work? Yes, it is. So I don't actually need to copy anything with the firm for this. So share firmware, Wi-Fi. Yeah, let's just start sync everything. Oh. Vendor firmware. This is 12.4. This should be 12.1, is it? Just 12.4. That. The firmware, I think Apple messes with it, but it's mostly the Broadcom firmware, but Apple customizes it. Okay, that should be good enough. I'm just going to reboot that now. Kill the hypervisor, and let's get the... yeah, I need to run our firmware extractor. Git Asahi installer, source, firmware, yeah. I think that's how yeah. Asahi git vendor. So now git vendor firmware 12.4 firmware. That's not right. Wi-Fi is it? No, firmware Wi-Fi. That should be there. I'm forgetting how to run this. $57. Maybe they changed something again. KVI split 1P. Yeah, the P stuff. Yeah, we grabbed these from the IPSW and the real installer. I'm just doing this because it's easier. Let's just see what's going on here. Assert. Wait. Oh, there's a freaking directory there. Why is there a second? Why is there a second firmware for this machine specifically? By the way, also this is 4378B3, which means the Wi-Fi driver actually is going to need a change because this is a different chip now. So that's a thing. It's just a different revision, so just going to have to get added to the table. But we'll see that in the log. It claims to be B1 43785, but I think this is wrong. We need B3 now. So that's different. Drivers, net, Wi-Fi, wireless, Broadcom, FMAC, and this is in the PCIe file if I remember correctly. 4378B1, yeah, so we need a B3 here. And indeed, yeah, we had this set to, yeah, it was 3 for that one. And this is going to be 5. Because that says 5. So in this case, if that's bit number 3, it would be like this. We don't know about 4, but I guess this is probably never going to be a 4 anyway, so. Yeah, but the TRX. Oh wait, no, that was a firmware, right? Yeah, okay. So I guess it probably is the just a debug build of the firmware. Yeah. So in this case, but then there's the perf thing though, which did get ignored. But we ignored that with. Oh, we're actually using OS walk, and then we find the. That's why, and then we find the other firmware in there. So I guess we don't actually want to do OS walk. What we really want to do. Oh, and it does if perf and dir name is here. That's where that goes. Yeah, you're right. Yeah, just do assert here. Sure. So there's our firmware tar. Make sure I move it out from here because I always need to remove that one too. I always forget to move files from here, and then during the I make like release builds of the firmware, and they have junk because it copies the whole directory. Vendor firmware, yes, might as well write that. And then in the init ramifs with firmware, firmware tar. Is this in the right directory? No. Yeah, that takes care of that. That should give me everything. Yep, Kyushu, that's this one. Looks sane. And Okinawa is apparently the new one. So that one, yeah, I guess the Air did get the... I like how we're still in Japan. It's great. So I get the fancy... As I thought, the new Air is basically an evolution of the Pro Max. So they're using that chip. And this one is an evolution of the... This one actually is just a new revision of the same chip from the old MacBook Pro, so they didn't even bother upgrading the Wi-Fi. So yes. How do I CPIO this? How did I do that? CPIO that. And then to create the with firmware, I think it was a cat gzip. I think it's just catted. Yeah. It's just zcat. It's not even zcat. This is right there. I can just cat that. Zcat. Genesis firmware at. Just do that like that. That should do it. And mini Linux. Let's try booting and see if we get Wi-Fi. Well, I don't have the tools for Wi-Fi, but I'm not actually going to test bringing up the Wi-Fi right now because honestly, it's gonna work. I'm pretty sure. So like if the interface comes up and the firmware comes up, I'll call it good enough. And then I'll just build I'll enable M2 support in the installer. That did not quite work, but it did go to B3, which is what we want. Kyushu. What is the file? I think a lot of those errors are normal because it's going to try a bunch of file names before it finds the good one. But it's possible that there's something different. So if I go here, what did you end up with here? We ended up with Kyushu. It's just Kyushu.bin. Please find V3 Apple Kyushu. Yes. Oh, I didn't find it. Oh, is this the non-firmware build? Init RAMFS with firmware. Yeah, that would help if I give it the firmware. That's more like it. That looks good. That looks good. There we go. There's a Wi-Fi interface. Let's just bring it up, see what happens. Yeah, it's not complaining at least. Yes, I don't have the Wi-Fi tools in the init RAMFS, but yeah, it loaded. We're good. I'm just gonna assume that's gonna work. We'll see once it gets, just build the real image. And besides, I have to build because I'm going to be doing a release real soon with some fixes for Linux. So honestly, if I could just dump in like super alpha M2 support in there, why not? So yeah, no, this works also as expected. So yeah, everything's going as expected. So let's kill that. Okay, next, SPMI. That's going to take us back to macOS. Let me also just commit that stuff in here. Git Linux Not those. Yes, those. Get the commit format for that. Do we need? I was gonna say I was wondering if we need the OTP stuff, but I'm assuming that didn't change with the with a minor revision, of course, because we don't check the revision number here. I'm pretty sure. Yeah, we don't. The revision number doesn't matter. So yeah, as long as it's the same chip, it doesn't matter if it's a slight revision. That looks good. Okay, so SPMI. So let's just trace that and see what sense it makes. So let's get that booting. Go to mini proxy client. Let me look at the ADT again. SPMI. Yep, nub SPMI 0 is the one we want because that has the main PMU. And that's easy enough to trace. Get that and continue. Oh, shit, I always forget to do that. Yeah, I have to click start. I should just fix that so like exiting the start console actually starts the guest. That's just so dumb. I always do that. There we go. Not much going on there. Shouldn't have much going on there normally, I think, during normal execution. But if I tell macOS to shut down, we should see something there. So I'll do that. Might as well see the shutdown sequence. I was doing some stuff. So we'll see the power down command in there. Yep, there you go. And now it died. Because it shut down. This does not look terribly different from the old SPMI, I think. So let me just turn it back on, and we can do the little experiment in Mini. So in let's make it work in Mini first. Mini hardware SPMI.py. Let's make this a bit bigger, and I'm just going to paste. We don't need this anymore. We already covered all that PCIe stuff. I'm going to look at the shutdown sequence because that's something of a relatively known quantity. And honestly, this sole SPMI thing needs a little bit more of... this looks pretty similar to the old one, to be honest. I know the regs are different, though. Not wildly so. So then we have the... Where was I? Let's look at the ADT that had the... So it definitely needs to write the... what was the bit for that for shutdown? I think it was leg scratch pad. is where that gets written. Should be F7. Yeah, look, F703, there it is. And F701. Yep. Read status. Okay, this looks very similar to the old SPMI. 8E30. That's right. L, yeah. I believe that's the PMU. Oh, wait a second. Is this just because we have the... Oh, this is hard coding the address. That's not useful. Let's fix that. Find primary PMU. Looks for novice PMI. PMU SPMI. Yeah. Stow is what this one's called. And it returns the path. So yeah, we just need to register. That's reg. Yeah, this actually works. Like I have the dash stuff hacked, so you can actually just do that. And this should just be byte 0 of reg self.reg. And so this is looking for, this was getting stuck on the reply previously. So it just, the command register looks pretty similar to me. Reg at the top, yeah, active slave ID 814, yeah. Command 0, yeah, that looks the same. That didn't change. And then it's reading. The reply is an 8. Status is a 0. And status RxMPTX empty. Yeah, that looks compatible to me. Is it just a slave ID? Hey, that worked. Okay, maybe this SPMI is not new. Never mind. Hello. T12 Apple SPMI. Let's just call it Apple SPMI. Maybe there is nothing to do here. Huh. Well, okay. Let's just try booting Linux with that. That was a lot more anticlimactic. I still need to reverse engineer SPMI properly because our driver is kind of a horrible hack right now. But it looks like it's compatible enough for this. So, yeah, let's just try that. That looks like the RTC works. I think it's fine. Mac SMC RTC, yeah. Setting system clock, yeah. No, power off. That doesn't work. That's F. That shut down. Yeah, okay, never mind. SPMI. Oh no, it didn't shut down. Interesting. It didn't shut down. It rebooted. So that didn't work. So something else is different. But maybe I just messed up the offsets though. Legacy NVMem is here. Boot stage, shutdown flag. We have that at F1. F701. That's F here, yep. And that is writing what run 004 bits 31. That is correct. So it didn't quite shut down properly. But almost. Oh, also, now in run guest, I can actually do that and stop having to go into recovery mode, which is excellent. Where... you know what? Let's just trace it. Yeah, that's rebooting us, which is clearly wrong. But what did we get? Compared with what macOS did. F707. F7OF. AE38. Yeah, that's right. That's the read. And then we write 8. Oh, maybe something... Wait, is the flag different? Oh, no, sorry, that's a read too. Yeah, because 38 is read. Yeah, so it reads. Let me just make sure I understand this right. SPMI regs status command. A read is a readl command, size -1. Yeah. Reply value. Yeah, it reads 8. So this is reading that. It gets 10E38 and then 0. So it gets a 0. So then it writes an 8. It's possible that it's not this flag. The problem is just the sequence is wrong. I had to power off something. Yeah, SMC shutdown. Yep, that's right. This does get the PMU. Let's just test this in mini while we're here. SPMI, PMU, MPMU. Yeah, just tries both, but let's just actually use this. Hardware, SPMI, hardware, PMU, import, PMU. Proxy client, tools, reset panic counter. Yeah, just this PMU. Might as well also do that. And then we just do s dot SPMI. Yeah, so it writes that bit 8 to the mode and then PM setting to 0. Let's just print it. The address. Yeah, we do get that right. Reg mode. PM setting. Don't need path anymore. Oh, yeah. Node PMU. That's... Oh, node PMU, sorry. Oh yeah, this is a PMU, sorry. So node. Yeah, dies now. Oh, wait, now it shut down when I did a force reboot, so that did work. Yeah, that actually works fine. Is Linux just doing something wrong? Yeah, it sets that to 8. That's right. Is it just too fast or like not polling properly? Oh, also because this was traced non-synchronously, so I think it might just be this driver's just kind of broken. Wait, this is doing write, read, read, write. That's kind of a weird. No, it does read that. Yeah, wait, read. I don't know why it reads it twice, but okay. Wait, read, and then writes an 8. I think this is just the Linux driver is broken and always has been. Because it's pretty bad. It's on the list to redo that one. Read status. Isn't this backwards? No, if empty, yeah, that's right, but the status is 0, and it's like it writes, then reads the reply, then checks. No. Okay, that's broken. Obviously, for writes, we need to uh wait for a reply. Let's look at what macOS does again. Because I might give some hint as to how this is actually supposed to work. So the way it does it is it first checks the status register, which you actually expect. So that makes sense. Then it writes the command and the data directly, and then it just reads. It reads some stuff which we don't know about, but these are probably like interrupt related registers. Hey, this is an interrupt flag because it's behaving like 1. Might as well just put that down. And then anyway, it's reading the status register again, which is different this time around. So this time we have TXMT was always there. RXMT is that one, yep, 24. And then this would be probably like RX count. And then it reads that. Then it gets RXMT. Yeah. So yeah, I'm pretty sure that's what that's going to be. So let's just say that right. X count would be... Yeah, so I said I was going to run a SPMI driver. I'm going to fix the existing SPMI driver. That would be 2316. And then this is probably TX count because it makes too much sense. I'm actually just totally guessing that, but there's a good chance that's it. And you can see that here it's reading, yeah. reads. Yeah, so the other thing is that the way we're doing this is we're just waiting for all the data to arrive, but that's probably not the right way of doing it. But anyway, yeah. For now, let's just make this driver not be broken. Writes the command, and this writes the data. Waits. Okay, this is wrong. This is absolutely wrong. So this writes the command, writes everything there. Yeah, okay, so this just has to be... Yeah, so there's still no error checking here. This all needs to be productionized badly. But for now... For now, that just gets... that'll work. Yeah, 8E... I wonder what 8E30 is. But yeah, this way of polling doesn't make any sense. Though it still should have worked. The 8... Yeah, it's still got that. Unless that's the old data, which it could be. No, it's just the command, right? Yeah. It looks like it should work, even though this is kind of broken. And then for the read command... Also, why is there like a 15 millisecond timeout? That's kind of weird. Status. Well, this is still better than yeah, but then it reads the place status, and then yeah, this one's more reasonable for the reads. The right one really needed that. For now, let's just do that. At least there's a timeout involved. But oh. But then why didn't it work? Because it should have. Because this looks correct. Let's check against macOS again. F8OE. Oh, wait. Did I just have the wrong address? No, F70 if it's there. F70 OE30. OE38. Oh, wait. F80C. I think I just have... I just had the wrong things in the ADT, don't I? In the device tree. PM setting is F801. Yeah, that's right. The X trackpad is F7. That's also correct. F7OF. No, that is right. No, it is right. Sorry. Then why F7OF 0830? Yeah. That's it. We are writing that. Maybe it's just a race. Maybe this is just bad data because it's not complete. Well, I mean, let me just try doing this again because maybe it was just a fluke. Status undeclared. This code needs clean up. I wonder if I should try like properly fixing this driver to use like interrupts and stuff, or leave that for another time. That did not work. Oh, now it's shut down. Okay, then maybe it was just that buggy driver thing. Yeah. Yeah, it could have just been that then. Does this have any decent logs? What was this exactly? Yeah, that makes more sense. Oh, and this should be write command also, but also we don't need that. Device tree is there. That should be fine. And just drop the hack, fix that up. Okay. Yeah, that works then. So really only touchpad and keyboard are left, which is actually going to involve writing a new driver, unlike this one. Let me just do a quick tweet. Because people like updates. Okay, that should be good enough. Oh yeah, Sven just pushed the whip Bluetooth branch apparently, because Sven has been working on Bluetooth and it works now. Okay, so now we actually get to write a new driver. Which is probably not actually going to be that hard. Let's see if I can get some little mini prototype going first. Turn it back on again, because shutdown works now. Oh yeah, I need to add this stuff. I did not see the tweet about the bad thermals of the N2 Pro, but didn't the M1 Pro also have bad thermals? Oh, sorry, no, that was the Air. Yeah, no, I don't know about that. Does it? I mean, I don't actually want this machine. Like, I only got it because it's the first M2 I could get, but I want the Air. I don't want the Pro. I don't need the touch bar. That's why I got the base model, which apparently also has a like bad SSD performance. I don't. This machine is weird. Okay, like really, I only have it so I can do this stream. And yeah, like yeah, I don't know. It's I don't know what I'm gonna do with it once everything works. All right, I can actually just quit Ghidra because I'm not gonna need that anymore. And I don't need these SPMI things either, because that all was a big anticlimactic. All right, so guest. I need something to trace Dockchannel. Am I really gonna need it? I don't know if I'm gonna make an actual tracer, but yeah, sure. Let's just make something. Like trace. Oh, this is a good one. Trace something small. Dart. Yeah. Of copy and paste here. From yeah, not actually have any tracers, but I'm just going to yeah, none of that is useful. Something small, a PCIe, yeah, that'll work. I do want I range. So trace device, 280T Dockchannel. Yeah, so UART is the one that we have actually seen. And then there's MTP, which interestingly has apparently a lot of Dockchannels. And they're all identical. So this looks like channel number 0, right? And then somehow we have a lot of, I don't know why it's done like that. If you're sending URLs that YouTube catches that and doesn't let you send URLs, I can't really like there's no option to let you through. It just eats them. AHD Hibernator. What on earth is that? Apple HID Transport Hibernator. Why is it called the Hibernator? Yeah, so we do want to have an ASC tracer for this. Actually, this should be called trace MTP. Trace that in verbose mode, then trace device, ARM IO, Dockchannel MTP. And just run macOS and see what happens. No, it means like multi-touch processor or something. Not, yeah, it's just an acronym collision. Oh, look, we have syslogs. Excellent. MTP says hello. Look at that. That's most excellent. Yeah, and so as I expected, it gets initialized once, and then nothing happens. Other than some syslogs, apparently. Yeah, so when I touch it, moves. Okay. I love when we get syslogs. It's just great. Look at that. MTP says hello. Version Apple MTP from Refu. IPD HID SPI attached. Mac Power Manager state machine initialized. ACT Manager init com multi-touch keyboard STM actuator TP Axel. Oh, is that why? Oh, because they literally. Ooh, okay. They literally use a different dock channel for every single thing in there. Okay. That's why. So that's why there's a pile of dock channel. Okay, that's interesting. And yes, there is nothing. There are no endpoints. This is the dumbest possible ASC device. There's nothing going on there. Everything goes over dock channel. Which is pretty much what I expected. So is there an actual accelerometer here? Apparently there is. That's interesting. Yes, press a single key. That's a good point. That's a lot of data for a single key. Oh yeah, but as you can see, dock channel is pretty simple. This is the count of bytes in the FIFO. This is the data in the FIFO. You actually get the count in the data register anyway, and then you get the data and the upper bits. And that's pretty much all there is to it. This one is probably the interrupt status or something like that. 8 at 404. And then you get a C. Yeah, so those are probably like FIFO empty bits. Oh no, wait, this is a different channel. It's writing C to 0. Yeah, so it's like I was expecting it to all go through a single dock channel. I wasn't expecting it to be multiplexed at the like not multiplex basically, to literally be using different dock channels for everything. So maybe the first one, that would make sense. So maybe the reason why there are where's my ADT? Yeah, so maybe the reason why there's two is because the first one has like global stuff, and then the others are the actual channels. Because it's reading from one. And then three. And then one again, and three. Yeah. And then writes to two, apparently, which is a bit weird. So we have the sub devices. Let me just copy that somewhere. There's a lot of data in the Dockchannel that time around. Yeah, it has like a... So I'm pretty the FIFO is pretty deep. I thought the UART one was only 256 bytes, but this one's apparently much bigger. Grape interface configuration completed. Interesting. Keyboard interface configuration completed. Keyboard ready. Excellent. Interface configuration completed. Axle ready. Do you know if the SPI also had this kind of init stuff? I will say, though, I bet you this is the first laptop you're ever going to own that is going to show you system logs from the Touchpad firmware in your Linux message. How cool is that? Once this works, I mean. So let's go to mini firmware. I mean, it's an ASC, but the ASC doesn't do anything, so we don't really even need an actual MTP thing. I guess it's hardware Dockchannel. What we actually need to make for testing. It's just a bit of copy pasta here. Bit of Well, macOS is also dumping these things in the syslog, so I sure hope they're not dumping keys there. Yeah. Yeah, so 2C is FIFO count. What about the writes? Where do writes go? Not the clears, but the actual commands, because there's some stuff that's going to be sent. You know it's going to send some packets. Looks like 10. Is it right in 32-bit chunks? I guess it probably just uses whatever. I don't think AOP actually has an accelerometer on some of the models. Like there's a spot for it on the board, but then it's not actually populated. I looked for that once. Um, 14. Yeah, that just looks like this is the right data register, and it probably actually writes in 32-bit chunks, because why wouldn't you? The reads are always byte-wise, though. So let's look at the key press. For the key press, it reads from 404, then it you got C bytes there, which are all mostly zeros, which makes sense because it's like an HID packet. F7, FF. Then it writes that to trying to understand what the different mappings are here. Where do we have? Where did I put the? You get the touchpad stuff. So we have this, and then we have the actual dock channels, which look like this. So we have 6 of those. Oh, and it is actually 6 ranges. So then there has to be 1-to-1. But com sounds like it could be special anyway. Also, that did have 1 interrupt only, I think. Yeah, it only has 1 common interrupt for everything. So this could be a bit mask of the channels that have data, in which case that would mean 3. And then it writes a C, which is a bit strange. But it's writing to different offsets, though, which is a bit weird. And then... write for, read for... Yeah, so that one's clearly, like, clearing that flag. I don't really get the C. What about the other touch, like, things? It's always reading from 3 this time around. Okay, that's kind of weird. Like, I see a lot of 3s, and I'm expecting more than that. Unless there's a mux involved. Which there could be. So maybe these don't map to these. Okay, let's look at the messages. Where it says initialized. Okay, that's when it writes to grape, which I think is 1. Which looks like that. So maybe that's just the red herring that it has all those register ranges, or it has to do with the mux, and it is all channeled over one of them. So we have that for grape, in which case it will be closer to SPI. Keyboard interface, this should be enough to tell us what's going on. Keyboard is 2. There is a 2 there. There is a 1 there. Yes. Okay, no, so this... the register ranges do not map to the channels that's done in data. The register ranges just... they're all used for different purposes or something. Let's look at the ADT again to see if there's any hints as to what they do. But they could just be... The interesting thing is that... Okay, let me actually get the UART. Which, of course, means zillion spams. But you can see, now this is a different dock channel. Which is actually a bit different. So for that one, it just writes to 14. Which is actually different, but almost. It writes to 4, sorry. It writes to 4. The 14 is the same. That's the FIFO, like, space free for writes register. And then it's writing to offset 4. Which is interesting, because that's not... what we get for the touchpad one. It is possible that this is actually not compatible, but... Because this one has a Dockchannel T8002 compatible. This one could be some other, like, different... Also, interestingly, there's an offset there, right? Which there isn't here. FIFO size is specified. So it does say channel number 0. Channel name, channel 0, whatever that is. Maybe there is like multiple registers for that. Because then there's that mux thing, right? HID transport mux. But that one's just like a random helper device, so I'm not sure if that's relevant. Interestingly, there's an IOMMU parent, even though I don't expect any memory like addresses being passed here. This one needs an IOMMU parent, which hopefully is the same. Yeah, 175. Okay, we have enough logs. I'm just going to copy and paste some of the keyboard stuff. Actually, I'm going to do it again because I'm going to actually do press and release of the 1 key. And I put a new line in there. So this is a key down. And I think we can kill macOS for now. So you know it's one channel anyway. We got some reads and some writes. That should be enough info. And time to poke around in Mini. Reboot. And to be honest, this PMU stuff should be done in setup.py so we can stop doing that manually. So, dock channels. So I don't know about the multiple ranges, but for now, at least this 2C, 1C thing, and so 3 is the one that has the actual data. So 1C is the read data, 2C is RX depth. And then we have the depth RX count. Just go to RX count. Let's just go to count our data. It is RX data, sorry. It's gonna be different otherwise. So the count is in the low bits. Data is in those bits. RX data, RX count. And then TX data is in 10. And there's some flags involved in the registers 0 and 4. And 14 is TX free. Let's call this Rx full. I think a lot of this is going to make a lot more sense when we start actually watching these registers. So let's go to shell. We're not even going to start the coprocessor yet. I'm just going to play around with the dock channels. Mon.add. Let's add a mon on 0, and on 1, and on 2, and on 3. So for now, that's not triggering any data. Okay, so we can tell that 2 and 3 are similar. 1 looks different. 0 and 1 look different. That's all zeros. Okay, let's just add everything. There's no 6. Oh, okay, interesting. So there are 4 channels, and then the first 2 are special. Which also matches up with the... What about the UART? Interesting. Oh, no, is this just looping? FE0, 8 FE0, CF0, 8 FE0, CF. Okay, this is just Apple specifying this. Yeah, Apple doesn't know how to do consistent device trees, okay? These are the same. It's just that in the UART case, it's all in one big register block. In this case, they specified them separately, but they both have the 4 channels. They just broke it up differently. And so the order is 0, 1, 4, and then 30, 30. Yeah. Oh, but wait, there's like different offsets. The offsets are weird though. 30, 34, 28 to C. And then the 0 and 14. Yeah, 30, 34. 30, 34, 28, and 2C. It's the same. They're just in a different order here. And then at 0 and 14, we have the... Oh, those aren't even there. So the Dockchannel UART is actually missing that. That kind of worked. Okay, so there's more than one Dockchannel thing here, but yes, 0 is special. And so let's add just a page here and that 14. Yeah. And I'm going to just add the UART. Oh, and that one has a C in there. Which is probably similar to... that one. So let's send some stuff out the UART. Interesting. So you can see how we can actually read those back here. So that you can see how the connection works. And these are just more of the read register, I guess, so you can do longer reads or something. So the UART only takes 8-bit reads, writes to this register. What about the 10? Is that a thing? Yes. Oh, wait. Yes. So there's an 8-bit read and yes. Okay, look. So here we got CC, which is the low byte because it's Little Indian. Then we should be getting A, B, B. So these are this is 16-bit read. And then this is probably no, there's no 32-bit read because that doesn't make sense. Unless you just read both. But then look, there's another one there. Yeah. 32, yes. So if I do 1, 1, 2, 2, 3, 3, 4, 4, and I read 32 from this one, EF80, and just get that. No, that didn't work then. Do I think you had CO10? Did I mess that up? FE. What am I doing wrong? Do I need to read another register to get something else? Do I need to read 1, 8? Uh, oh, it's possible that something else is dumping the UART out. Oh, I think that's what it is. I think there's some other agent pulling from the UART. Yeah, I think so. Yeah, that's it. See, you got 44 there. So if I pull from 20, we get 3, 3, 4, 4. If I pull from 24, same thing with an 80. No, 2, 2, 3. Oh, you can get 24-bit bunches out? That's interesting. Yeah, that really is 24 bits. What, 28? That's just pulling 32 bits, it looks like. What if I read 64? Yeah, same. Can I write 64 here? No. Yeah, so 24 is reading, yeah, cool. And that starts to fill out all the registers, which is cool. TX10 is TX32, we know that. And then the TX1 was, which one was it? Four, which makes sense. If I write 32 to 4, we just get the 44. Yep. If I write to 8, we get both. Yep. And if I write to C, apparently that... Oh, you get some reading 16s here. Yep, we get 2A. And if I write to 10, yep. So it's exactly the same. Cool. Easy. See, it's like it looks like weird when you first look at the traces and then you poke around the hardware, and this makes perfect sense, and it's perfectly logical. There's nothing weird about it. And this is a Dockchannel. Excellent. Though, as you can tell from the address ranges, they are interconnected in different ways. So it's not the the registers in one block are not linked to each other. They are, like cross-connected or something like that. So in this case, so in this case, 2C00 is sending to 3400. Does it go in the other direction? Because that would be very symmetric and sensible. It sure looks like it. Yep. It goes in both directions. That's easy. What about the others? We have registers at 2C and 28. So if 2C is connected to 34, I would expect 28 to be connected to 30. That did not work. Whoa, that really broke. So DC is connected to 34. 28 isn't connected to anything, apparently. Unless something is just pulling so quickly that we can't see it, which is possible. 34 is connected to 2C. And 38... Yeah, it's possible that something else is just pulling so quickly that we don't see it. So let's try the MTP dock channels, because MTP is not up now in theory. So let's send some stuff here. That didn't do anything. Interesting. So 34 is connected to C indeed. Yep. And yeah, I don't know what 28 goes. Quite interesting. Anyway, this is writing to 34, which is the one connected to 2C, so that makes sense. Unless these only have support for some of these simpler, like write 8s. Wrong address. Oh, wait, that's... They're just stuck there. Oh, okay, that's different than... That's... Okay, those are different. Those are not symmetric then. Yeah, okay. So they are... It's not 4, it's just 2. Each dock channel is just one FIFO pair. It's just that there's something else going on here. Yeah, AD081C, AD011C. Yeah, there's... I don't know what these are at FE8. It could be like a version number for the hardware or something like that. Okay, so the other thing we can do, which is kind of cute, is memset32. Just set all the bits to 1 and just see what happens. Set everything to 1 in 28. And as we can see, there's not that many registers there. That's good. It's easy. And clearly, these are settings of some sort. Dockchannel is looking very simple. So yes, we don't know what 28 is. Let's call this Dockchannel data regs. So now the next part is the interrupt flags. We haven't seen anything about that yet. So I think some init happened to make that work. So we did memset32 on those ranges. Let's look at these at the top here. Let's set a page of that. Okay, now we can see what that does. And at 14, there was something else. Oh, look at that. Stuff happened. Let me actually only add the reg 0 and reg 1 because those look like control regs, and otherwise I'm just going to be clearing the FIFO status in those. That's not doing anything though. Okay, I'm going to reboot because the memset probably didn't help. Let's get it all cleaned up. Add regs 0 and 1 to the mon, and then if I write something now, nothing happens. Nothing happens. There was a mask involved in the... no, I added mon for MTP. It was intended for MTP. I am messing with MTP now because the UART is... There's some kind of system agent pulling stuff from the UART, and I don't want that to get in the way. The MTP one is idle now because I'm not actually... I haven't booted the thing. So let's see how this initializes things from the log here. The first thing it does is this. And it does write to the control regs, and then it just starts going. So that's the init sequence. It's reading 2C, which is the bytes. Yeah. Let's call this Rx count. And then it's writing C to 4 and then 8. That's probably an interrupt mask. Then it gets an... or the 0... both could be interrupt masks. I get the feeling that 0 is the interrupt mask at 14. And this is writing 8. That doesn't do anything. It didn't even write. 4, sorry, 8. At 0, if I write at 0... Yes, okay, that's an enable, clearly. And then if I empty the channel by reading 28s, for example. Is it actually empty? 24? Yeah, it is empty. Okay, that's not actually changing with the interrupts, though. Oh, because it's already... Okay, that's not actually doing anything. At the end of the sequence... Right, C and 8 to 4. Yeah, it is empty. Is it doing anything else? Oh, 30. It also has to poke with 30. That's getting written. So that's the per channel status. Ah. Does that get written at the top? Yes, sorry. That needs to get set to C. So in that case, let's actually add reg 2. And then if on that one I write at 4, if I write a C, that gets written. And now if I send some data through from the other side, I bet we'll see something. No. Interesting. So at 1404. Okay, so that's a flag because it's clearing it. The other one is like an enable. 1404, the flag is 0 now. The enable is 8. Let's get this to C. Okay, that gives me a flag. Actually, you know what? Let's just set this to, like, everything. Interesting. Only that one bit clears, I guess. Yeah, interesting. Set everything onto there, because why not? And then on 2C and 28. Oh, that didn't work. Oh, FFF. Oh, it's just not monitored. Yeah. And then at 34, clear that if we... Oh, okay, that's a config. That's not a flags. So we are saying that to everything. So let's just set that to everything. And now if I send some data, is anything going to blink? Nope. I feel like something is missing. Let's look at the log again. Oh, right, so 50 there. That one's new. Okay, let me look at this a bit more carefully. So it does then it starts reading data. And then at the end of the... Not even at the end of the data being read, because there's still data there, but... But at the end of that read operation, I guess, writes 50 to 4. And then an 8 again. No, at 14. So we have a C50. That's an interesting... Those are kind of interesting numbers. So if we write 50 to... We write that. Doesn't read anything. Let's see if it does anything else interesting. No, it's 50, but then it reads again without writing 8. C, sorry. What about the next? Then he writes a C again. Then it more reads. Then it writes a 50 again. C again. Is it possible this is like a mux? No, because the FIFO is the same though. I'll be right back. Just one sec. Sorry about that. Okay, let's do another reboot. Look at that again. Let me actually write a script to try to replicate what's going on here. I'm just gonna copy and paste this. No, that's not even useful. Let's call that one unc on the 1. Seems like we're mostly messing with those 4 registers. Um, let's read in 16-bit chunks. Oh wait, there's nothing at 0. We're not touching 0 in the end. We're only touching the control and data. Maybe we just had the wrong numbers. Got that wrong. Yeah, so nothing really changes there other than the receipt count. Actually, I'm gonna remove these because it just makes it harder to read. So control plus 4 is 25, which is interesting. We're not touching that though. Actually, I wonder if those are like control for both sides, because we don't touch 0, we touch 1, 4. They also look kind of symmetrical, and then it's like it adds up to 28, which is the beginning of the data channels. So that actually makes sense. So if I write... So how does it end? At the end of a key press, it ends with writing 8 to the data, to the, like, that thing, and writing 8 to the... Yeah, to both of those. So... Still nothing. Oh, 48, no, not 4804, sorry. And then we need to write C to control plus 4. Oh, the 50 business. Yes, I'm working on the keyboard. I wonder if this just doesn't work because we're missing some kind of global enable that the MTP is in charge of flipping. That would explain things. Oh, wait, I'm also... Duh. Oh, okay, there we go, look. 8-0. That cleared it. So that finally let me clear the... That finally let me clear that flag. At 4. Does it have to end at 50 for that to work? Nope. What was it? It was 0. Oh, look, that... At 0, the 8 flag comes back. And then 1 makes it go away. Oh, is this a FIFO threshold? Could be a FIFO threshold. That would actually make sense. That would make perfect sense, actually. Yeah, that's what it is. Yeah, it's a FIFO threshold. Okay, that makes sense. Cool. And the other one is probably the transmit FIFO threshold. See, everything makes sense in the end. Yes, see, we writing 16 bits. We set the threshold to 2, then it triggers when it's... If I set the threshold to 3, then it doesn't trigger. And if I write 32 bits, then it triggers. Oh, sorry. Let's try threshold to 4. It doesn't trigger if I write 32 bits. It does trigger. Cool. So now the other one is the... So then, if I'm thinking about this correctly, I bet 8 is one of the interrupts, and if I set this to, like, FF, we'll see more things. Yeah, there's obviously more than one interrupt there. You can see that the... I should just print all these in binary. Yeah, so that one means FIFO has some data. Let's fill up the FIFO just to see what happens then. Doesn't seem to change. It's the same as before, so it's not like there's an overflow. Now, what about the other direction? Interesting. That 0 one is not a threshold. Interesting. Whatever I write to it ends up being shifted up. Oh no, it's just because I have an A there. No, yeah. So that probably is a threshold. Any idea why Apple changed the way keyboard trackpad work on M2? Well, you should wait for our progress report, because I actually wrote up most of that already, but I just wanted to actually write the driver before releasing it. Before publishing it and doing some other stuff, which is why I'm doing this tonight. But yes, there will be an article about that coming out soon. Okay, so if I write there you go. There's another bit. That bit 4 is the transmit threshold. Yeah, okay, so bit 4 is transmit flag, and this is the number of bytes you want to be free in the buffer before that. So if I set that to like 7E8, should stay up. Yes, and if I say 79, yeah. So that is correct. Did I mess that up? Yeah, Rx data is fine. So then we have bit 2 means TX thresh. Bit 3 means RX thresh. Interestingly, all the other bits are 1. And they stick there. So I wonder what those represent, if anything. Maybe it's the other direction. It doesn't make a lot of sense, though. Did this one behave the same thing? CTL plus 4? No. So that is a bit different. So these could be the other direction flags. Nah, nothing happens when I touch those. Maybe they're just like not implemented and they just ended up being like that. Maybe it's just, like useless silicon. But there have to be flags for the other side though. So and obviously those aren't actually so I wonder what those are. You just go to the shell again. Just do a bit of experiments. Add 0 and 1 to here. Oh, because that has the flags disabled. That's why. It probably does work then. If I just write... oh. Interesting. That only flipped some bits. Okay, so maybe those are actually a control section. In that case... Yeah. Interesting. Interesting. There's nothing... So that one isn't accessible. What about 8? Which pages can we access? That one we can. That one we can't. That one we can. So it goes to 18. Oh, that looks... like 8,000 might be the flags. Yes. And interestingly, there's another register there, the next one over. Wonder what that's about. At 8. Okay, there's just F there. Let's just try writing those, see what happens. Where was that thing I saw? The like at 8. That's not working anymore. Oh, it's not control straight. I said the flags. Yes, okay, so those do get set, but other than those don't seem to affect anything. If I just leave it at F, does anything happen? Doesn't look like it. Yeah, maybe it's just those two flags. So what about the other side? The other side is never getting its flags set. But what are its thresholds? Oh, okay, something happened there. Ah, okay, so the flags are on both ends. Yes. So the flags are completely symmetric. I think the top bits are just BS then. Or maybe it's for some other Dockchannel like this goes on or something. There's just two sets of flags for the different sides. I don't know what the other thing these do. Maybe it's some kind of delay or something like that. Doesn't seem to affect anything. Yeah, it doesn't seem to do anything. Yeah, okay. So that I think that answers all the questions. Um And then we have 28. There we go. That's pretty much what there is to it. Now, these registers are hardware in the M2 that is used to communicate between the AP and the touchpad controller, which is now in the M2, which is why this is all different now. It's not really channel 0, it's like ARX and BRX. And that means our device tree binding is fairly simple because it just means that we just need to specify 3 ranges, IRQ, FIFO, and data regs for our side, whatever our side is, and that's the Dockchannel. And then we also need to specify the IRQ flags bit offset for the to know which side we are, which in this case would be 2. And that's pretty much everything that there is to it. I don't understand doc w stat mask. Oh wait, that's the no, it's not the FIFO size. Because the FIFO size is 800, which is 2048. Unless that's for the thresholds. Yeah, that might make sense. Maybe that's for the maybe that's the mask for the threshold value, because the threshold value can go up to the full FIFO length, so that would make sense. And then there's a channel number, which, you know, whatever, but I'm not sure if that's relevant. Okay, that there's our Dockchannel. So the UART one is interesting because it goes to 28 and then 2C, and 28 is one of the sides. It's the different side from the one used by MTP. But then what about C? What's that C? Oh, that's another set of interrupt flags. Okay, how many sets of interrupt flags do we have? Are there 4 channels here? It looks like it. Maybe there are 4 interrupts out of this. And maybe not all of them are used. Does it go after 14? Oh, there's more of those. Okay, that killed it. So maybe there is more than 2 sides to this. Or maybe there's just more interrupt registers. Oh, yeah, that kills it. Oh. Oh, sorry. Wonder what FE0 is then. So 18 killed it, was it? No, 18 is fine. So it looks like there are actually 5 channels of some kind. So then what about the rest of the registers? So 18, nothing. 1C exception. 20 exception. 24 exception. 28 exception. 28 works. Yes, we know those. 2C, 30, 34, 38. Okay, there's more. So if I write to the next threshold registers, aha. Oh, sorry, these should be zeros. See, this is the next one. It's over. Yes. Now the other flags are getting cleared. So that looks like it's actually a separate set of FIFOs. So there's 2 FIFOs per Dockchannel set. So if I write to channel 1D plus, that should give me something on that end. Yes. So in this case, we are writing, we're changing the thresholds first at that end, and then changing the other thresholds. Okay, I'm still a bit confused here. These two are not actually symmetric. Those 2 bits are, but the others are not being set the same. And actually, it doesn't make sense that they're set the same because we have thresholds for... This is still a bit weird. Okay, I need to actually... I'm going to clean this up a bit because it's getting too confusing. So we have 5 interrupt register sets, apparently. Actually, let me just go to shell. Mon add. Let me set everything. Yeah, so those are... Oh, wait. Yes. Oh, okay. So, like, 8 is special. And then there's C048. Oh, so maybe 8 is different. And then the actual interrupt registers are C048. That would make sense. Oh, interesting. Writing to... Oh! That enabled register set 8000. More things there, because now it behaves like the others. You can see what changed there too. Because that only had bit 1 set before, now it has more. So is that 8? C was 100. And then 10 was 0. And if I write to 8,000... no, that's not clear. Oh, that. Nope. And then I wonder about that FE0 stuff. So if I just set just memset all the things. That also does nothing apparently. Okay, yeah, so 8,000 is obviously special because it's not quite the same as the others. Okay, that does end there, so it goes to 44. Yeah. So we're gonna set the transmit threshold to 800, so that as soon as there, so the flag clears as soon as there is any byte in the FIFO, and then we're gonna set the receive threshold to 1, so it sets as soon as there's any data in the FIFO. Actually, no, we're gonna set the transmit FIFO to 7FF, so that actually to 7F0 even. F8 maybe, because that will. Yeah, something like that. No, I can just get rid of all this for now. So we're gonna pull. It's gonna give us some interrupts. It should be all the transmit interrupts. That didn't work. Oh, DC plus base. Oh no, that's fine. Oh, 4020. Oh, I'm not rereading that. Yes. Okay, so those all flags are set. That's the transmit flag for everything. We don't need this anymore. So then we write to the transmit 32 register. Pull. Send another 4 bytes. Pull again. Okay, so we send on that one. Let's just so 28 ends up at 30. And we can see that the threshold isn't quite. Oh, because I'm off by this 9. Yeah, so it's 9. No, not quite. Oh, maybe there's like some implicit. Oh no, it's just because of the Hmm. Yes. So after sending those, that one is the same on all the interrupt registers. Then we get the data, and yeah, that sets that bit. Okay, so this is starting to make some sense. So we have all the interrupt flags look like they're symmetric. For some reason, there are 5 sets of registers. So let's just do one for now, so it's a bit easier to see. Yeah. Yeah, okay, that makes sense. Cool. So what we end up having is one A, one B, two A, two B, and so those are the sides, right? So these would be 2A transmit, yes, because that gets clear there. Yep, that one gets clear there. That's the transmit for 1B. Then this one, yeah, it's exactly the same. Okay, so that we can see the symmetry here now. There are there are 4 FIFOs connected in pairs between 2 entities, and there's 2 sets of those. And so each entity has 2 interrupt flags and masks, and also there are separate interrupt registers. So in principle, any entity could be listening on any other entity's interrupts, but only one of these would be mapped to the AP's interrupt. Presumably the one that this one is using, which was which one? And we'll see that too in the AIC probably. So I should look at that. Let's yeah, let's look at the hardware state on AIC, see if that makes it. But actually, all of these are going to trigger though, because we're setting all the flags. So I can probably just do that manually. Let's only do, because that's the timestamp. Yeah, that should do it. And then if I look at the interrupts there, so there's nothing there. C 10, 14, 18. Okay, nothing's triggering interrupts now. Oh, probably need to clear the flags for 4FF. Yes. That cleared one interrupt. That's 6860. And then this one clears another one. This one doesn't do anything. That one doesn't do anything. C. That one was on there too. Which one am I missing? 18? Yes. So 18, C, 14, and... Wait. I already did 18 twice. Why did that clear one and then the other? Was that just a random fluke? No, I don't believe that was a random fluke. Wait, what did it start off as? A 6820? Oh yeah, that probably was a random fluke. Yeah, I think that was a random fluke. Okay, yeah, so we only have two of them. The 18 and 14 ones. Yeah, so A and B are the two sides of a channel, and there are two channels. And two sets of interrupt registers go to AAC. Two sets probably go straight to the ASC. I don't know what the global ones do, but one of them seemed to have something to do with that register set, the 8000 one. Let me just try writing to the global regs, see if they mess up the interrupts or something. If I enable these, and then in the global regs, let me just add a mon for this, for the globals, and for those. Can you write these? I don't think you can write these. No. Wait. That was wrong. I think those are like ID regs or something. So the global ones. I can clear them. Didn't change the interrupts. And 18, 14, yeah. I clear these. Yeah, it clears the ASC ones. Yeah, I don't know what the global regs do. One of them seemed to do it with that C interrupt set, though, because it did something to, like, enable it. But macOS never touches the global ones anyway, so I think we can just ignore them. Let me just reboot. So the trick now is going to be representing this with the silly way Apple did it in the device tree, because it's not consistent. But we do have... So the UART one has the FIFO, the status regs first, and then the FIFO is implicit, and then it has the interrupt regs after that, one set of them. The MTP one has the globals, which we don't know about, then the interrupt regs, and then the and then the other stuff. So the PManager stuff was... He is writing to 2C, which is the data regs for the first set. So it is different from yeah, it is the set that starts there where the Also the length is wrong there, if it's the same, which I hope it is. So let's just try running the same experiment, but on the UART Dockchannel. And just to make sure that it... No, not shut down. Why did I just shut it down? Well, that's good. I can restart it now and see if it still works from a clean start. This is what I want to run. Let's try the UART now. Oh, interesting. There's like more stuff now. The flags, there's more flags. Maybe there are more UART doc channels. They do work as I expect, though. Or maybe these top bits are just garbage here. Maybe there are many doc channels, though, in this one. That would be interesting. Interestingly, I'm getting C0. Oh, no, it's because I only set this to C0, right? And the... Let's get all of them. Yeah, definitely getting... Ooh, there's different... different flags there, though. Yeah, so 8000 is clearly a bit special in some way. Do we have more doc channels here? Yes, we do. Okay, so the UART one, there's many more. Which probably means these are used, I bet, by like as virtual UARTs for the for different peripherals or something like that. There's a lot of doc channels here. And yeah, look, 8000 is a bit special somehow. Like all the way to here. No, that is errors. But interestingly, there's still only this many interrupts. There should be more for this one then. Yes. Oh, not that many though. But I think some of these might just be protected. Yeah. Yeah, that 4 there is nothing there, but the others, yes. So this one has at least 6 interrupt register sets. The first one being a bit special, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 dock channels. Well, wait. They're pairs though. How does that work? It does work, yes. Not 15. Did I count wrong? 14. So 7 pairs. Yeah, so 8,000 is a bit special there. They are still all symmetric. But some things are masked from some of those. They are still all symmetric. They are still all behaving the same way. It's just that some things never get set in some of these registers. So there's some kind of masks involved. So let me just add the base for that. Oh, okay, look, there's... That looks like individual enables for different channels. And so we have at least 7 channels, but it looks more like 8. And how many register interrupt registers? We have at least 6. So let's check these 8,000 ones. Oh, wait, I'm missing... Oh, no, I'm not. Okay, so it really is 7 dock channels, because that's how many register sets we have. Like interrupt flags. And then only the bottom ones are getting those bits set for... Oh, is it these? Ooh, it rebooted. Oh, okay. Some coprocessor tried to use these dock channels and really hated what I just did there. So yes, they do use them. I wonder, can we pull them and get like debugs from coprocessors? That would be fun. I bet that was SMC crashing right now, by the way. It's like the only thing that uses these. Okay, so let's just do that again. Add that, add the 8,000. write the enable flags for that. Yep, that gets those, but it's missing those at the top. And now, if I write to, I bet it's that one, to 10 here, 14. Yes. No. No, it's 10, sorry. Yes, look at that. Do these clear? Oh, but they don't clear anymore, though. Maybe this is like an update enable. Because that definitely enables those. I can kill it. And then if I run this experiment. Ah, yeah, look. Some of those are stuck now. So I think it is some kind of update enable. And now they work. Yeah. So if I kill that one, that still seems to work. Oh, does it? Yeah, it does. Yeah, you do get all the flags. So I'm not sure what that first register is for. But it's clearly related to this. That one doesn't seem to be writable. 8 is writable. That's interesting. Wonder what that one does. Maybe that's for the 4000, which might be like a protected register or something like that. Because I get the feeling that at least one of these is like for the SEP or something, and that's why I can't access it. The one at 4000. Yeah, it looks like it basically all works now, so. Okay. I think that answers all the questions we need to know. We don't need to touch the globals, most likely. And if we ever do we ever can always just do that in Mini. And then as far as Linux is concerned, we only care about an interrupt register set and an agent register set, basically. So, as far as this is concerned, so this isn't really IRQ flags at this point. It's just yeah, it can go bigger. So So UDT path channel or agent, as we say. In this case, I guess this isn't all that useful as the ADT path. So let's just say you IQ base, FIFO base, IQ index. And then we can just say so if IQ equals reg map data regs, FIFO regs. Sorry. Yeah, FIFO base would be FIFO regs, data regs. Let's go config regs. Config regs, FIFO base. How do we call these reg maps? I forgot. We need it's UN base. Thought so. Self config, self data equals base 1000 and IRQ base. Okay, and so now the actual algorithm, and we're not going to do the IRQs here, but just for actually we can property So we were just going to clear all the flags initially and then return I forgot which one was first, the RX or TX. TX is the bottom one. Okay, and then we're going to have a Line 58 config data. Oh yes, thanks. So left line data, while as long as we have at least 4 bytes of data left, then we do while there's less than 4 bytes left in the transmit buffer, do that. So I left this greater than or equal than 4. Get a word out of that. Put it in the transmit register. That should do that. And then do the byte-wise. I'm not going to do 16 bits. This is writing in those low bits. Yes, it's just writing in low bits. This is not a property. Probably not ever going to use these except for experiments, but might as well have them. So this is how you write. And now we read. Number of count bytes. Actually, for receiving, we might as well use the 32-bit one. Append. There's no pointer there. Just left. While left is greater than 1. X count is less than 1. Pass. And then RX8 actually has data. Read all. All right, there we go. That's our Dockchannel implementation, our proper Dockchannel implementation. And so now, if I let's create a new experiment. This would be called MTP.py. And so what we do Standard ASC is in the ASC. We do need a Dart on this. DCP, how does DCP do it? Uh, Stream's okay, right? Oh. Interesting. Audio's okay, right? This didn't die or anything? Because my pulse audio on my streaming machine did die. Wonder how that happened. I guess no more music for me then. Is that Spotify there? So yeah, I don't use Pulse Audio for the actual stream, so that doesn't matter because it's on Jack, but apparently Pulse Audio died really badly. I mean, the touchpad has firmware on every machine. Every touchpad has firmware. You need firmware for, like, touch detection. It's just that they now moved a lot of the interesting code into the M2 instead of having it in the touchpad. But touchpads have always had firmware since the dawn of time. Okay, so that should initialize our touchpad processor, and now we create a Dockchannel. Which needs to be initialized like this. And in this case, the index is 1. And the registers for the interrupts here are register set 1. And the FIFO base is, well, 2 and 3, but we consider them as 1. SMC address, MTP address, yes, thank you. And so now, and now what I can do is Look at, did we have a thing? Did this only do mons or? Yeah, I think I have yeah, there's a run shell, and I probably should just have a poll thing here. Yeah, let's just do that. That'll be useful. And then I can go to MTP and let's say always read syslogs when that happens. And now we can play around with the Dockchannel. So, that is not working. Interesting. Do we need to PManager this? It's possible. Let's see how it actually, wasn't it like this has the is running thing. We are calling boot on it and it's not booting. What did this one do? Mac OS. Yeah, it did set CPU control run 1. It might be a PManager thing. Just make sure that this is actually enabled. No. Oh, and there's not even in, it's not even in PManager. Interesting. So that's not actually booting. Why? Oh, do we need both? No, it should get a hello. It should get a hello. Is this the outbox control issue? Do we need like an enable there or something? MTP get reg 0. Mini get reg 0 on hardware ASC. Outbox control is 8114. It is already set to the same thing. 200. Yeah, it is set to that. Interesting. Why is this not booting? Is there some other dependency? No clock gates, no power gates. MP version is 1. Roll MTP. No firmware service. Sleep on hibernate. Reloaded 1. The usual interrupts. Does have an IOMMU. Is it possible that we need to map something in the Dart before this works? Let's trace that too. Guest. I think I didn't do that. Ah, yes, it's not this. It's dash M trace MTP. Okay, it does initialize the Dart first. We don't have a good tracer for that, I think. Do we have a tracer for the Oh, we do. Well, mostly just uses the regs anyway. Dart 8110 tracer. Let's actually have that. Yeah. Okay. We did, yes. Reads a bunch of stuff. Okay, so it does set up 4 streams. No, only the first one, though. And in fact, I'm guessing this one only supports 4 streams. This has 16 SIDs. But this only does 4. It does enable translation for that one. Does something that we don't know about. Does not try to enable any streams, though. Oh, interesting. And it starts with TTPR1. So it's stream 1. But this happens after. It happens after the thing starts booting, though. And it doesn't even have a TTPR at that point. It only gets a TTPR after it starts mapping things. Also, the SID should match here in that case. MTP mapper, yeah, reg 1, so it is on 1. And I guess I need to specify the SID on that to make that make sense. Mini hardware dart 810. Yeah, instance, not instance 0. So what I need is stream. Did we have a thing for setting that in ASC? Oh, it's hard-coded to 0. Well, that's annoying. That needs fixing. Mind you, that still doesn't explain the problem, though. It is possible that this is a DABF problem, though. Because I'm not sure if we're even tracing that. Let me just reboot. And I'm actually going to do a normal trace on that. See if there's any DABF stuff. Wrong index on get reg for which one? Oh, the Dart, you're right. The Dart is 1. No, both. That's the DABF probably. So I bet that's the problem then. Yeah. Yeah. I bet we need to set the DABF stuff up. Otherwise, it won't work. Because it doesn't have. Oh, okay. It has translate enable. No TTBR, but no bypass. So I bet this is set up via the DAPF. Yeah. Pretty sure that's what's going on. And so then the DAPF is in charge of the firmware stuff. And that is getting set up here. And so those are these, the DAPF instance 0. AOP.py. Yeah, that looks about right. Yep, that looks about right. I'm not sure if there's any arguments involved. I wouldn't be surprised if there aren't any arguments for this one. But yes, the DAPF needs to be set. We should do that in Mini. Is this the same thing then? The exact same thing? 4HC 1014. It's not 4 exactly, but 8C 1014 31 is getting set. Oh yeah. The 0 8C 1014. This doesn't seem to get set. But 8C 1014 does. And 20 does get set to 2. Wait, 30, 0, 40 is 31, yeah. So 60 is set to 2, yes. Eight C 1014, and these are, what is that firmware data? Are these the same then? Is it the same format? Wouldn't surprise me if it is. That looks like an address. That's yep. From to UNC1, UNC2 to UNC1, UNC2 from. That's not right. Okay, it's not quite the same. There's more stuff in between here. And what gets written is 3100. Presume the C is that one. UNC1, this is 64, UNC1, 34. And then 5, 32-bit or something like that. And then this is having 8C, 1014, yeah, those look right. And then 0 is 31, 20 is 2. Unc 1. And that 31 could be this. Let's reboot that, see if that boots the MTP. Where am I? That did not work. It is setting them. Could be that we're not enabling translation yet. Or it could be that we need one of the other magic things. There's a diag lock. There's nothing interesting here. Then it does the TCRs, but these shouldn't matter right now. Oh wait, no, this one might matter. One probably actually needs to be set. This is probably going through the DAPF2. So that does AOP do that? Yeah. So let's do that one too. Start regs DCR1 set by yes. Let's do that. DCR1. Oh, why am I already doing that? That's dumb. I might as well let it run now and get another trace. Still not works. calculating this properly. Oh, this is UNC1, not UNC5. Oh, yes, it works now. Cool. Dockchannel. FIFO base. Get reg 0. Let's get that. Reboot that again. Yeah, we should really just make mini set up the APFs from the ADT. Nix doesn't need to care about that. Interesting. That really didn't like that. Those are syslogs. Don't need to print this. Okay, there we go. Now we have that. Woo! Unmapped page at Hervier. Interesting. Oh, it's pre-allocated. But how? There's no TTBR. How can it be pre-allocated? What does macOS do here? Yeah, it just gives it a... Oh, wait. Isn't that a physical address? Yes, it would be. And so... Which makes sense, because I kind of expect this to use some kind of SRAM or something. So it's probably using the Dart for some extra stuff. And so then in that case, there should be some kind of VA map or something. No, it's not segment ranges or anything. VM base is really low. VM size is like 4 gigs. That probably gets set in the DAPF. What is that? Yeah, it's... So in this case, we need the DVA is getting ANDed with that for IO reads. That's actually not correct in this case. We need the DVA offset 0. So it basically be IO read. So I can do something like allow face and DVA is less than DVA offset, or DVA is greater than self DVA offset plus size. DVA data. I translate. Oh, this is just outright wrong. Yeah, something like that. And then here in MTP, I can just do allow is true, and then hopefully, yes, startup complete. Look, syslogs. Initializing common interface 1 multi-touch. It stops there. Interesting. After exactly 8 messages, that's a bit suspicious. Did I miss something here? Oh, let's count 16 though, so. So if I read everything, yeah, we got some data there. And now, can I initialize that? Can I write? What we have is C1, sorry, 08, 08, 11, OC00. 180 000. That should be the whole packet. No, I think it's stuck. I think something is missing. No, I think it crashes after multi-touch. Oh, I know what's going on. The GPIO. There's a GPIO involved. This one, because that's multi-touch. GPIO 8 on the SMC. So SMC needs to be up for this to work. Because I bet that needs to go low for this to not explode. And that, if it's a reset, I don't know which one it should be, but it's going to be one of these. It's either that or the with the LSB set there. Oh, interesting. That time it just stopped on that one. Oh, 08, sorry, I'm dumb. 08. No, that didn't work. No, it's still not working. Interestingly, it got worse when we had the SMC. Oh, now I got further. Okay, this is just not consistent. It's not the GPIO. Yeah, if I do it quickly, it's worse. Yeah, some sort of something weird, yeah. No dart errors, at least. Are we not hacking things right? There we are, just doing the usual hacks. Why are we getting 2 startup completes though? That's a bit weird. Is there some confusion going on here? Oh, because you call wait boot twice? Oh, yeah, yeah, because you got it twice. That doesn't actually matter. Yeah, something is wrong here. Let's just do a bunch of work. Yeah, like if I do it fast, it breaks even faster. That's interesting. It's almost like the syslog replies aren't what it wants. Let's trace macOS again and get a bit more debug out of this. Verbose to Trace MTP. Yeah, it is set to verbose 3 and oh, MTP tracer. It is set to verbose 1. Let's set it to verbose 3. Run that. Is it just never acking the syslogs? It just acts them later. Let's kill that and look at both traces carefully, see what's different. Could be that IO report thing, to be honest. I got some stuff in there. Duty cycle, power state. Yeah, it definitely wrote that, so that's fine. Is there a crash that we're not getting? No, the crash buffer is empty. So what macOS did is after the Dart stuff, hello, hello ACK, EP map. Starts 1, 2, and 4. Yep. And then it gets the buffer thing. From EPO1, that's the pre-alloc. Gets a buffer request. comes back with a DVA. Here it's C8. IO rep start, and then yeah, the reports. That's 7 on management. Yeah, it's the power state. And then we send. Wait, we send endpoint 1? Interesting. So it does actually send the crash log buffer. I thought we weren't supposed to do that when it was pre-allocated. Let's try that. No, that didn't help anything. Yeah, it doesn't matter if we send it back. Wait, 1.4. Yeah, it didn't actually help. Yeah, it definitely crashes. More things that this is doing. Could just be some Dart things too that, like, you know, one of these magic brights makes it stable or something. And like that's the end of the IPD HID SPY thing, right? And then after that, goes off to some other things. Eventually, it comes up with the Mac Power State Manager thing enabled, and then it receives more syslogs. Could be one of these Dart settings, to be honest. Uh, Let me just dump some of those things in here. Oh yeah, I mentioned the boot targets. Yeah. I'm not actually tracing the firmware ranges, so I probably should. But first, let me just make sure that it's not this Dart thing. Nope. So how are the boot arcs done? It looks at the firmware base. Oh, that's one of the regs. No, it just has the 2 regs. For EO5. Just in case, trace MTP, Dart MTP. Just trace the whole thing. Run guest again. I'm gonna log this. And just those copy and paste of the Python things, just to rule out all the Dart stuff. It initialize. Yes. Oh, it does. No, it just reads from Dockchannel that time. It reads from Dockchannel, then it writes the Dart stuff. The only writes are the TCR. Let's just brute force it for now. Oh, is this the enable streams thing? It does the hello stuff, then after the first map, it enables things. Let me just enable it from the top. Let's see what happens just with that brute force like that. Nope, that's still not helping. Instead, if I do it slowly, it like works better. It's really weird. It just dies after a while, basically, but yeah, it's not consistent. Well, it's not a timeout issue, it's just the other way around. If I do it fast, it like dies faster, so that doesn't make sense. Let me just trace those DVAs also in the trace MTP. Where's the IRIP one? Let's just do that much. It's also possible that it just doesn't like that dart range that I'm using here. Let's try a smaller IOVA range. But it did write stuff there though, so like something started to work at least. Huh? Oh. Yeah, I guess we need past that. Let's get some KWRs in there. Yeah, that doesn't help. Okay, let's trace that again. Just to see if it's doing anything with that memory. Oh. It didn't work. Trace MTP. Got parentheses. Are there any GPIOs involved? Oh, there's another one here. STM reset. Right. Let's trace SMC also, because that could tell us something. The SMC stuff is happening. A lot of it as usual. Okay. Should be enough. Let's look at the log. MTP. Adds the endpoints. It's already reading the syslogs there. HID spy attached. So SMC actually gets initialized after that, after the HID spy attached thing. The interesting thing is that that's one point where it stops, and then it continues. So maybe there's something we need to do to make it continue. Because then SMC comes in after that. And as usual, there's a lot of random crap. Then we get more MTP messages, but no GPIOs. Oh, wait a second. Is this a bug in here? It doesn't look like, because we do check after that, but let's actually wait for that to drain before sending more. Shouldn't really make a difference, but no, it just stays there. Oh, and yeah, you can tell that now it hangs because nothing's reading that message. It's not this, is it? Oh, was that it? Oh, that was probably it then. Ah, that's interesting. Okay, that answers another question. So the CPU control flag is like the thing that tells the CPU to boot. And I think what's going on is that it's going into low power mode itself. And so if this isn't left set, then it never comes back. Yeah, that's it. Okay, so that answers yet another question, which is whether we should leave that turned on or off. Apparently, we need to leave it turned on for some ASCs. But we need to make sure we turn it off when we shut things down. Otherwise, they will start back up, and that's a bad thing. So basically, then that explains the algorithm is basically turn this on, leave it on when running. Then, if we're going to shut the ASC down, we issue a shutdown. We turn this off after the shutdown command. Then we issue the PManager reset. Another corner case figured out. Okay. In which case, okay, now let's get rid of all this junk, because that has nothing to do with anything. Okay, here we go. Now, we get those logs. And now I can do dockchannel.readAll. We get that. And then I can write that. Look, grape interface configuration completed. Excellent. We get some other stuff. Keyboard interface configuration completed. That one is almost the same. Just replace the one with a 2 there. And then it's 2 before. And C1EB. Oh, that's a checksum, isn't it? I think that's a checksum. Yes, keyboard interface configuration complete. Keyboard ready. Will it actually reply to keys? Yes, I get key events. Okay, the keyboard works. Yay! Okay, I think this is a good point to stop because it is 4:30 a.m. here. And clearly this works. I have to look at the actual protocol, but it's probably the same or very similar to whatever we were doing over SPI. So that means the next time I just have to write a Linux driver for this, and then we are done, and the keyboard and the trackpad works. No trackpad yet. Yeah, if I do like yeah, I don't have the rest of them here, but yeah, obviously this is working fine. Okay, I need to get some sleep. That was see, I'm happy that Dockchannel, like, this is exhaustively reverse engineered now. It's not just do what macOS does. I know what every register does. I know that when I write the driver, it's going to make sense. And I know that this is common for the UART and for the MTP Dockchannel. And so I can write a generic driver that I know is going to work for both. And I can write device tree bindings that I know are going to work for both. And so that's very good. Okay. That's I'm going to add these inits to the script so I can play around with it. If I can just go to MTP before I leave, I can just write these things down. And just show you that it can like autonomously handle things. Yeah, there you go. Keyword works. Pressing keys. And it is obviously an HID packet because that's what keyword HID packets look like. Oh shit is caps log, yeah. A function is like a different flag there. That's interesting. I assume that's already figured out. But it's probably in the descriptor anyway, so. No touchpad, because I need to do those inits. But yeah, I mean, obviously that's going to work once I get that. So cool. All right. So yeah. Yes, we need Dockchannel HID. I wonder how much code it can share with SPI HID. Maybe it can be so I think there's going to be 3 drivers. There's going to be a Dockchannel driver. There's going to be a Dockchannel consumer that is for HID, which may or may not share code with SPI depending on how close it is. And there's going to be a MTP driver that just does the ASC stuff and needs to be tied to the SPI stuff somehow, but it's not terribly critical, I guess. So yeah, something like that. Okay, I needed some sleep. But this means we're basically done reverse engineering the M2. There's just one more one small set of drivers left to write, and then it's done. M2 is as good as M1 at that point. All right, see you next time. Thanks for joining. How many people did we get? 83 people. Come on, this was like an... Oh, no, wait, that was the old one. 49 people for an unannounced stream. That's pretty good. So yeah, see you next time. I'll get some sleep. Bye.